Hello, everyone. I'm Li Yue from DeepSeek, the corresponding author of this paper. Today, I'm honored to share our journey and insights we have gained over the past 3 years while developing deep learning training clusters equipped with 10,000 of A100 GPUs. My presentation will focus on cost-effective hardware and software architectures for deep learning, which have played a crucial role in our work. Let me quickly introduce our company, DeepSeek. We are an AI startup, and we improve the attention mechanism to create the multi-head latent attention architecture. We've used this in our MOE large language model, which boosts performance and reduce KV cache usage. Today, I'm excited to announce something new, the DeepSeek R1 Night Preview model. It matches OpenAI's O1 preview in reasoning tasks like math coding and complex logic. Plus, it goes a step further by showing the complete thought process, which O1 preview doesn't review. If you are curious, check it out at chat.deepseek.com. Okay. As deep learning's need for compute power increases almost tenfold each year, we are facing several major challenges. First, rising cost. Second, energy consumption. Third, scalability and stability. To tackle the cost issue, we developed the Fire-Flyer AI-HPC architecture designed specifically for our deep learning. It helps us meet our training needs at a much lower cost. Here is the outline of this presentation. First, I will start an overview of the Fire-Flyer AI-HPC architecture. Second, the software stack, including HFReduce, HaiScale, HiPlatform, and the 3FS file system. Third, networking tuning to reduce congestion. Fourth, class stability. Finally, outlook and the future work. Let's look at the architecture of each GPU node, which adopts AMD Apex CPUs to 11 PCIe lanes. Each node contains 8 NVIDIA A100 GPUs and a 200 gigabits InfiniBand link. We initially didn't include NVLink bridge connector, but we added later to better handle large language model training tasks. Let's dive into our network topology. We adopt a dual symmetric fat tree topology, as shown in the figure. Our set features a unified compute and storage network, meaning both I/O storage and GPU compute traffic use the same unified network. This setup reduces the costs associated with east-west and north-south traffic. Our platform's scheduler can redirect the loads for large tasks. This smart set ensures that only one pair of interconnect links is needed to manage cross-room traffic, keep things streamlined and effective. Let's explore the cost-effective PCIe architecture of Fire-Flyer. Our GPU node is economically designed, costing only 60% of what a DGX A100 would. We use this special 2-layer fat trees instead of the 3-layer fat tree, and it makes significant reduction in network cost. By unified compute and storage traffic into single network, we avoid the need for separate resource. Additionally, using an 800-port chassis switch help us Additionally, using an 800-port chassis switch help us cut down on the cost of interconnection cables and optimal transceivers significantly. Okay, now I will introduce HFReduce, our PCIe topology-aware allreduce communication library. Similar to NICO, we propose HFReduce to tackle PCIe's bandwidth bottlenecks, especially with 8 GPU and a single InfiniBand NIC. We also find that no CPU utilization during training, so we offload reduced computation to CPU, optimizing performance and resource utility. Here is the details of HFReduce. First, we perform intra-node reduction. Data is transferred from the GPUs to the host memory, where the reduction is optimized using SMD and NUMA-aware access. Next, for the inter-node reduce, we use infinite band warps with RDMA write and apply the double binary tree or reduce algorithm to efficiently aggregate data across nodes. Finally, the reduced data is sent back from the host memory to GPU. Let me briefly explain the key HFReduce advantages, as shown in the bandwidth figure comparison with nickel. First, PCIe bandwidth savings. The CPU performs reduction within nodes. The total amount of data is half compared to nickel. Next, GDR copy speeds up small size by enabling direct CPU to GPU writes, reducing memory overhead. For large data transfer, pipeline the execution process data in slices, improve performance across nodes. We also use NUMA-aware optimization to balance throughput and latency through smart memory binding. Lastly, there is no kernel overhead as the CPU handles reduction and communications, leaving GPU compute unaffected. Together, these optimizations make HFReduce highly efficient, especially for large-scale operations like ones displayed in chart. Once we install the NVLink bridge, two paired GPUs gain direct high-speed NVLink connections. This allows us to reduce data directly between the GPU before running the standard HFReduce operation. By doing this, we cut the data sent to CPU in half, significantly improve performance, as shown in the bottom right chart. HaiScale is a parallel tool optimized specially for PCIe architecture. It is a drop-in replacement for torch distributed data parallel, requiring just a single line of code change. For large model training, we implement optimization especially for loads with a single NIC by assigning the 8 GPUs on a load to separate data parallel ranks. We maximize bandwidth utilization during allreduce operations due to the high bandwidth within the same node. Additionally, we strangle pipeline parallel communication times between GPUs to avoid bandwidth contention and reduce congestion. Let's review the training performance of Llama 13B model and our DeepSeek MOE 16B model after applying our optimization methods. The config is in the slides. For Llama, it achieved 92% strong scalability on 256 GPUs and 82% on 512 GPUs. For DeepSeek MOE model, we reached 93% strong scalability on 320 GPUs, but it dropped to 76% on 640 GPUs, as shown in the chart. Our optimization results in excellent scalability with a few hundreds of GPU. Okay, let's look at the Hai platform, our custom scaling platform for training tasks. Unlike traditional supercomputing systems, they rely on swarms for job scheduling. We've developed a time-sharing container-based scheduling mechanism. Containers on the Hai platform can be launched and start running in just 10 seconds. And our custom scheduler can interrupt and resume tasks actively using modal checkpoints. This flexibility allows the system to dynamically assign loads based on task priority. For example, higher priority tasks can seamlessly preempt nodes running lower priority tasks. For LLM training, the checkpoint manager ensures smooth fault recovery. It efficiently manages model parameters and optimizes status, while leveraging 3FS file system and 200 gigabits NIC throughput to save and load large models in seconds. Additionally, it auto-saves checkpoints every 5 minutes, keeping training loads to a minimum, even in the event of a fault. Together, these features enhance the platform's scalability and fault tolerance. HFReduce, HaiScale, Hai platform, and 3FS file system form an integrated framework seamlessly embedded into our training platform. Researchers can focus on their models without worrying about hardware, as the optimized performance helps speed up model training. Next, my colleague Shang Yan will talk the other part of this presentation.
Hello, everyone. I'm Shang Yan from DeepSeek. First, let me briefly introduce the 3FS file system. It is an all-flash distributed parallel file system with each storage node equipped with 16 SSDs and two 200 gigabits InfiniBand NICs connect X6. The two InfiniBand NICs are connected separately to two factory zones. File reads and writes often involve many-to-one communication, which poses a risk of in-cast congestion. To mitigate this, 3FS adopts a request-to-send flow control mechanism. Before a storage node sends data back to the client via RDMA write, it first receives explicit credit from the client. While this step introduces minor latency, it effectively limits the number of in-flight requests and helps reduce network congestion. In result, with 180 storage nodes, 3FS can achieve a peak storage bandwidth of 8 terabytes per second. In addition to the 3FS-related congestion mentioned earlier, our network has another major source of congestion. This is caused by OpenSM, which doesn't support our non-standard factory topology, resulting in traffic collisions. We addressed this issue with a custom routing algorithm. You can find more details in our paper. As mentioned before, since we only have one NIC per node, to prevent network traffic from different applications from interfering with each other, we map HFReduce, NICO, 3FS, and other traffic types to separate virtualize and preventing interference and resolving head-of-line blocking issue between various traffic types. We also configure quality of service to ensure file bandwidth allocation, balancing the network performance between 3FS storage and allreduce communications in training. Next, let's discuss about the congestion control and adaptive routing. The InfiniBand NIC Connect X6 only support DCQCN congestion control algorithm. For the distribution, it is hard to find a group of parameters that work fine for HFReduce, Nico, and 3FS at the same time. Moreover, we observed that enabling distribution reduced the peak network throughput, so we disable it. Regarding adaptive routing, we found that it could lead more severe congestion spreading across the network, so we also disable it. Thanks to our optimization mentioned before, both 3FS and HFReduce perform well without enabling congestion control or adaptive routing. Here is a quick summary of our Fire-Flyer AI-HPC architecture. We start with low-cost PCIe node and special network topology. We use HFReduce and HaiScale for scalability, and the 3FS file system provides strong storage support. Our network optimization enhances traffic flow, and the Hai platform offers powerful training capabilities. All these components work together to form our robust architecture. Next, let's talk about how we keep large classes stable with smart fault analysis and recovery. Faults are unavoidable, but we aim to minimize their impact on users. In our class, silent errors like those missed by ECC happen more often and need to be detected and addressed quickly. For example, issues like ECC or NVLink errors are logged as XID errors in the kernel. By handling this efficiently, we ensure smooth and reliable operations. Let's dive into our fault analysis focused on GPU issues. A big chunk of our GPU errors comes from XID74 NVLink errors. This is something we keep a close eye on. For nodes with XID74 related NVLink errors, we run additional stress tests before the standard validating tool to ensure their stability. When it comes to ECC errors, we send the GPU for maintenance right away. We have seen over 200 GPUs with ECC issues, which is quite significant. For software-related errors like illegal memory access or illegal instructions, it's rare, but sometimes this can be due to some hardware errors. So even for these software alerts, we also do hardware health check after the error occurs. Understanding these patterns help us manage and mitigate GPU issues effectively. Let's take a look at the network faults, specifically link flapping in our InfiniBand network. Our data shows that link flapping happens almost weekly, and there are no any obvious patterns. To tackle this, we are replacing optical transceivers and cables with active optical cable, direct attach cable. We also switch from box switches to chassis switches. Our approach to boosting node stability is validating tools. The key is catching issues before they happen. We have developed tools to check if hardware is working as it should. Our automated system runs these checks weekly on each node. If a node has problem, it will be removed from scheduling. The invalidating tool comprises hardware health check, CPU and GPU gym performance check, benchmark, NVLink bandwidth test, and storage bandwidth test. It's simple but very useful. Our Hai platform can perform automatic recovery, removing faulty nodes reallocating resources, and automatically resume tasks. Thanks to the high performance of 3FS file system, the checkpoint manager can save checkpoints every 5 minutes, ensuring that if something goes wrong, we limit the training time loss to just 5 minutes. Therefore, our platform achieves high availability. Finally, let's discuss our future step for PCIe architecture. For communication-heavy scenario like MOE with intense all-to-all traffic, one GPU, one NIC ratio is ideal. We plan to implement a two-layer multi-plan network, which will be far more cost-effective than a three-layer network for large-scale systems. We are also considering moving from InfiniBand to Rocky to reduce infrastructure cost while maintaining performance. These upgrades aim to make our architecture more scalable and cost-effective. Thanks. That's all. Thanks for your time and attention.
Okay, and yep, here's a question.
Thank you for the interesting talk. I'm Hua Huang from NVIDIA, and since you have mentioned about Nickel and compare your implementation and algorithm with Nickel, probably I did not get all of your details, but you mentioned that you like have the communication size or something in the allreduce. Would you please explain a little bit about the difference in algorithms, your code and Nickel, and further, is that your algorithm can only be used for reduce. Can it also be applied to other collective operations? Thank you.
Okay, that's a great question. Sorry. Yeah, the Nickel is widely used in deep learning training, and our HFReduce is specially designed for PCIe architectures. So, the main difference between these two is HFReduce is entirely by the CPU. It has no GPU kernels, where Nickel requires GPU kernels for execution and communication. Secondly, HFReduce performs reduction in 2 steps. First, within the same node, and then across nodes, but Nickel doesn't. And for intra-node reduction, HFReduce effectively performs an operation similar to SHARP, that's NVIDIA SHARP. So where the GPU only needs transfer a single copy of data to CPU, and on the other hand, Nickel uses for example, ring or reduce algorithm, which requires about double the amount of data transfer. This is a key difference between the two approaches. And for the other type of collective operations, currently our HFReduce is support allreduce only, but we plan to support reduce scatter at a broadcast in the future. Thanks.
We have time. We'll get to both of you.
Hello, you were focused on the PCIe system, so I'm curious about can non-PCIe systems also benefit from the idea in your work? Thanks.
Okay, thanks for your question. Yes, our platform is suited for every systems. This work is mainly focused on PCIe system, But the other components of the platform, like HaiScale, High Platform, and 3FS file system, they are also compatible with non-PCIe systems.
Yeah, thank you. So thank you for a very nice talk. So can you give more details on the software errors? I think there seems to be much more than the NVLink errors. They are more than 50%.
Okay. The NVLink errors like XID 74, which logged in Linux kernel logs. This means interrupts in NVLink, and there are many types of this error, but the most of the time it is unaffected the higher level application. If it affects the higher level application, you may see unrecoverable error in kernel log. So if you find unrecoverable errors, you need to interrupt your application immediately and restart from the previous checkpoint and rerun it and remove this fault node.
Yes, thank you. So what about the software errors? The software killers like XID31, XID43. This seems to be also a lot in your runs.
Let me take through this slides. Okay. Sure.
It's not this one. So yeah, this one.
Okay. The most of the software related issues is by the software cost. It's maybe the code box or your something else. But the hardware field, like the memory is run now, so your code running in a wrong way, and it may be occurred software errors. It's not your code error, it's hardware execution error, and occurred a software error.
Yeah, so does this cause like the system to be rebooted or restarted from the previous checkpoint?
No. Yeah, sometimes it causes system reboot, but sometimes it causes snide result error.
Okay, thank you.
All right, any other questions? I don't see any online either. So in that case, let's thank both speakers.
Thank you all.